If you look at the night sky on a clear, dark evening far away from city lights, you will see thousands of tiny twinkling dots scattered across the darkness. These dots are stars, some closer, some much farther away. Some stars appear brighter, some dimmer, and some even have a faint color, red, blue, or yellow. If you take a step back and squint your eyes, you might notice a soft milky band stretching across the sky. This is our galaxy, the Milky Way. It is a huge spinning city of stars, gas and dust. Our sun is just one of the 100 to 400 billion stars that live in this galaxy. But what is most fascinating is that in the center of this grand star city there is a monster, not a monster like in stories, but a supermassive black hole. Its name is Sagittarius A, or SCRO. It sits about 26,700 light-years away from Earth. A light-year is the distance light travels in 1 year, which is roughly 9.46 trillion kilometers. To give you a sense of scale, if we tried to reach SCRO A** with a spacecraft moving at the speed of the fastest rocket ever built, it would take over 1.5 billion years to get there. Sagittarius A* is a black hole with a mass about 4 million times the mass of our Sun. Imagine 4 million suns crushed into a space smaller than the orbit of Mercury. This is hard to imagine, but it shows how extreme a black hole is. Its gravity is so strong that nothing, not even light, can escape once it gets too close. This is why black holes are invisible in normal light. They trap the light around them. We cannot see the black hole directly with our eyes. However, we can see how it affects its surroundings, especially stars and gas clouds moving near it. Astronomers first discovered the existence of Sagittarius A* in the 1970s. Using radio telescopes, they detected a bright point of radio waves coming from the center of the Milky Way. Later, as technology improved, astronomers used infrared and X-ray telescopes to see the stars orbiting around an invisible object. They noticed that some stars, like the famous star Solstice II, move in extremely fast orbits, circling the black hole every 16 years. Solstice can reach speeds of up to 25 million kilometers per hour, which is about 3% of the speed of light. This incredible speed tells astronomers that a huge mass must be pulling the star, confirming the presence of Sagittarius A*. To understand SCRO A*, we also need to understand its environment. The center of the Milky Way is not empty. It is filled with a thick mixture of gas, dust, and stars. This region is called the Central Molecular Zone, and it contains millions of times the mass of our Sun in gas and dust. Some of this material slowly falls toward the black hole, forming a structure called an accretion disk. The accretion disk is a swirling, spinning disk of gas and dust that gradually spirals into the black hole. As it moves inward, it heats up and glows brightly in X-ray and infrared light. Occasionally, this material produces sudden flashes of energy, called flares, which can be seen by special telescopes. These flares are like cosmic fireworks and help astronomers study the black hole indirectly. One of the most amazing things about Sagittarius A* is that, unlike some other supermassive black holes in the universe, it is relatively quiet. Some black holes, called active galactic nuclei, devour material so rapidly that they produce enormous energy, sometimes outshining the entire galaxy. Sagittarius A, on the other hand, is calm in comparison. It eats slowly, allowing stars near it to orbit safely, though still at astonishing speeds. Scientists study Sagittarius A carefully because it provides a laboratory to understand black holes without extreme destruction. To study this invisible monster, astronomers use some of the most advanced tools ever built. They use telescopes that can detect radio waves, infrared light, and X-rays, which are all invisible to human eyes. Radio telescopes, like the Very Large Array VLA in New Mexico, capture long radio waves emitted by the hot gas around the black hole. Infrared telescopes, such as the Very Large Telescope VLT in Chile, can see stars behind clouds of dust that would block visible light. X-ray telescopes, like Chandra, detect high-energy flares from the black hole's surroundings. One of the most advanced instruments is gravity, which combines light from multiple telescopes to see the tiniest movements of stars orbiting SCRO A*. With these tools, astronomers can measure the mass of the black hole, the shape of star orbits, and even test Einstein's theories of gravity. Let's take a closer look at the star Cell 2. Its orbit is not a perfect circle. It is an ellipse, meaning it gets closer to the black hole at some points and farther away at others. When Cell 2 comes closest to Sagittarius A*, it feels the strongest gravitational pull. Its light stretches slightly because of the intense gravity, a phenomenon called gravitational redshift, predicted by Einstein's general theory of relativity. Observing this helps scientists confirm that gravity behaves exactly as Einstein predicted, even in the presence of a supermassive black hole. Besides stars, Sagittarius A* occasionally interacts with gas clouds. One famous gas cloud called G2 passed near the black hole in 2014. Scientists expected it to be torn apart and produce a huge flare, but surprisingly, it survived. This taught astronomers that Screw asterisk is less active than they imagined, and that our black hole is unusually calm compared to other galaxies. If we imagine Sagittarius asterisk up close, it is a swirling, glowing disk of gas and dust surrounding a dark center. The outer parts move more slowly, while the inner parts spiral rapidly, heating up millions of degrees. Occasionally, the black hole releases jets, streams of particles moving near the speed of light, though Screw-ass jets are much smaller than those seen in active galaxies. These jets carry energy far into space and can affect star formation in the galaxy. But why should we care about this invisible monster? Sagittarius A* is not just a curiosity, it is a key to understanding galaxies and the universe. Almost every large galaxy, including our Milky Way, hosts a supermassive black hole at its center. These black holes influence how galaxies grow, how stars form, and how gas moves. By studying Screw A*, we learn about galaxies millions of light years away. We also learn about extreme physics that cannot be replicated on Earth: gravity, magnetism, plasma, and light at its highest energies. Sagittarius A* also helps scientists explore some of the biggest questions in science. What happens at the edge of a black hole, where gravity is strongest? How does time behave near it? How do black holes grow, and how do they affect the universe? By observing Screw A*, we are learning answers step by step. Every new observation gives us clues about the unseen, mysterious forces shaping the cosmos. Looking at the night sky, it is easy to feel small, but through tools, observations, and curiosity, we can understand the invisible monster at the center of our galaxy. Sagittarius A* is millions of times heavier than our Sun, surrounded by fast-moving stars, hot gas, and dust. It challenges our understanding of physics and fuels our curiosity. The next time you see the Milky Way stretching across the night sky, remember that at its heart lies a supermassive black hole, quietly shaping the destiny of billions of stars, including our Sun. Studying Sagittarius A* is not just for scientists. Anyone can be amazed by the numbers: 4 million suns in one place, stars moving millions of kilometers per hour, flares that brighten the invisible night, and the bending of space and time itself. These are real facts, grounded in decades of careful observation. The universe is extreme, astonishing, and beautiful, and Sagittarius A* is a perfect example of its mysteries. Understanding this monster is the first step to exploring the cosmos. From Earth, we are tiny observers, but with telescopes and imagination, we can follow stars, track gas clouds, and glimpse the invisible. The night sky is not just pretty, it is full of data, movement, energy, and secrets waiting to be uncovered. Sagittarius A* teaches us that even in the darkness, there is structure, rules, and incredible phenomena that challenge our understanding. One of the most interesting things about Sagittarius A* is how scientists can study something they cannot see. Because black holes do not let light escape, we cannot take a normal picture of them. Instead, astronomers watch how stars move around it. Stars near the center of the galaxy orbit Sagittarius A* very quickly, some taking just a few decades to make a complete orbit. By measuring their speed and path, Scientists can calculate the mass of the black hole, proving its existence without ever seeing it directly. This method was first used in the 1990s, and since then we have watched stars like SA2 orbiting Sagittarius A** at speeds of up to 15 million kilometers per hour. These observations gave us the first real confirmation that a supermassive black hole sits at the Milky Way's heart. Sagittarius A* has another strange and fascinating feature: its event horizon. This is the boundary around the black hole, the point of no return. Once anything crosses this line, even light cannot escape its gravity. If you imagine the sun shrinking down to a point where it is only about 12 million kilometers across, that would be the size of the event horizon of Sagittarius A*. Anything that falls past this invisible line is lost forever to the black hole. Around this boundary is an area called the accretion disk, where gas, dust, and sometimes stars swirl around the black hole at incredible speeds. This material heats up due to friction, glowing brightly in X-rays and radio waves, and that is what astronomers can detect from Earth. Even though Sagittarius A* seems quiet now, it wasn't always like this. Scientists believe that millions of years ago it was far more active, swallowing massive amounts of gas and dust and even small stars. During that time, it emitted enormous amounts of energy, creating a region of space that was brighter than thousands of stars combined. Today we see only the quiet center, but evidence of its violent past can still be found in massive clouds of hot gas and mysterious structures, like the Fermi bubbles, giant outflows of radiation extending tens of thousands of light-years above and below the galaxy. These bubbles are thought to be leftovers from Sagittarius A*'s explosive activity, a reminder of its tremendous power. The influence of Sagittarius A goes beyond just pulling on stars nearby. Its gravity helps shape the entire Milky Way. Without it, the galaxy's central bulge, the dense star-packed area near the core, might not exist in its current form. The spiral arms of the Milky Way, the regions where stars form and shine brightly, are also affected indirectly by the black hole's gravity. Even though the arms are far from the center, the overall stability and motion of the galaxy are tied to the mass of Sagittarius A. In other words, this black hole is not just an empty monster in the middle of space, it is the anchor that holds our entire galaxy together. Studying Sagittarius A* also gives us clues about other galaxies in the universe. Almost every large galaxy has a supermassive black hole at its center. By understanding ours, we learn about the processes that shape galaxies, star formation, and the cosmic evolution of matter. Sagittarius A* is like a cosmic laboratory. Its relatively quiet nature allows astronomers to study black hole physics up close without being overwhelmed by violent activity, unlike in galaxies with highly active black holes that consume enormous amounts of matter and produce blinding light. Technology has played a crucial role in revealing the secrets of Sagittarius A. Instruments like the Very Large Telescope in Chile, the Keck Observatory in Hawaii, and the Event Horizon Telescope have allowed scientists to observe the motion of stars, the glow of the accretion disk, and even begin to map the magnetic fields around the black hole. In 2022, the Event Horizon Telescope released an image of Sagittarius A, showing the shadow of the black hole against the glowing gas around it. This was a historic achievement, confirming decades of theory with a visual representation, even though the black hole itself remains invisible. Sagittarius A* also teaches us about the limits of physics. Inside a black hole, the laws of space, time, and matter as we know them break down. The singularity at the center, where all its mass is concentrated, is a point of infinite density. Here, general relativity, the theory Einstein gave us, can no longer fully explain what happens. This makes the black hole not just a cosmic object, but also a profound puzzle. Scientists use advanced simulations and mathematics to try to understand these regions, but so far much of it remains mysterious. Despite its power, Sagittarius A* is not a threat to Earth. It is too far away, and the stars orbit it in a stable way. Our solar system, 26,000 light-years from the center, is safe. The black hole's gravity only dominates the very core of the Milky Way. Even if it were more active, The radiation and energy would take thousands of years to reach us and would likely be spread out across the vast space, minimizing danger. Sagittarius A. Asterisk also affects the life cycle of stars. Stars that wander too close may be stretched and torn apart in a process called tidal disruption. The material from the star can spiral into the black hole, producing bursts of energy that are detectable across the galaxy. On the other hand, its gravitational pull also helps compress clouds of gas in the galactic center, leading to the formation of new stars. So, in a way, Sagittarius A is both a destroyer and a creator, influencing the balance of life and death for stars in the Milky Way. Finally, Sagittarius A reminds us of our place in the universe. It is a humbling thought to know that at the very heart of our galaxy lies an object so powerful and strange that we cannot fully comprehend it. Yet, through careful observation, patient study, and remarkable technology, humanity has managed to peek into this dark heart of the Milky Way. We have measured its mass, tracked its stars, and even glimpsed its shadow. Every discovery brings new questions, and every observation deepens our understanding of the galaxy we call home. Sagittarius A* is more than a black hole. It is the central engine of our galaxy, a cosmic anchor, a laboratory for physics, and a teacher of the universe's extremes. By studying it, we learn not just about a distant object 26,000 light-years away, but about gravity, matter, energy, and the delicate dance that allows billions of stars, including our own sun, to move in harmony. In the sky above, it remains invisible to the naked eye, yet its presence defines the Milky Way in ways we are only beginning to understand. Every star that twinkles, every cloud of gas that drifts, and every orbit that traces a path around the center of the galaxy is part of the grand story written by Sagittarius A*. Gravity near Sagittarius A* is unlike anything we experience on Earth. On our planet, gravity pulls us down with a force we can feel in every step. Near a black hole, gravity becomes extreme, bending space and time itself. Stars near the center of the galaxy move at astonishing speeds, some as fast as 15 million kilometers per hour. That is more than 12,000 times faster than a jet flying over Earth. The orbits of these stars are not simple circles or ellipses, they are elongated paths twisting and turning due to the pull of the black hole. Astronomers have observed stars completing full orbits in just a few decades, an incredibly short time on a cosmic scale. Watching these stars move is like seeing the invisible threads of gravity at work, tracing patterns we cannot otherwise detect. One of the most fascinating aspects of Sagittarius A's gravity is its effect on matter falling toward it. Gas and dust that wander too close are stretched into thin streams by tidal forces. This process is called spaghettification because the material stretches like a piece of spaghetti. When stars get too close, they can be torn apart entirely, sending a flood of gas and debris into the black hole. This violent process releases enormous amounts of energy, visible as X-rays and radio waves from Earth. These events are rare, but they are the cosmic fireworks that reveal the hidden power of the black hole. Even far from the event horizon, Sagittarius A's gravity shapes the galaxy. The central bulge of the Milky Way, a dense cluster of stars surrounding the black hole, owes its existence to this force. Without it, stars in the inner region would drift apart, and the galaxy would lose its shape. The black hole's gravity also influences the spiral arms of the Milky Way. These arms are vast regions where new stars are born, gas clouds swirl, and clusters of stars form. While the arms themselves are far from the center, the overall stability of the galaxy depends on the mass concentrated in Sagittarius A. It is a reminder that even unseen forces can have a direct impact on what we observe in the night sky. Gravity also affects the temperature and density of gas clouds near the black hole. In some regions, the immense pull compresses gas clouds, raising pressure and temperature and triggering star formation. In other areas, the black hole's gravity pulls matter away, preventing stars from forming. This delicate balance shows that Sagittarius A* is not just a destroyer, but also a creator, influencing the life cycle of stars on a massive scale. Scientists have discovered clouds of gas moving at hundreds of kilometers per second near the galactic center. Some of these clouds will eventually feed the black hole, while others may collapse to form new stars. The gravitational effects of Sagittarius A extend even further, influencing objects we rarely think about. Compact stellar remnants like neutron stars and white dwarfs can be pulled into unusual orbits, sometimes even flung outward at incredible speeds. These hypervelocity stars travel so fast that they may eventually escape the galaxy entirely. Their journeys are direct consequences of gravitational interactions with the black hole and surrounding stars, offering scientists unique opportunities to study physics under extreme conditions. Observing these gravitational effects requires incredible precision. Astronomers use telescopes like the Very Large Telescope (VLT) in Chile and the Keck Observatory in Hawaii to track the positions of stars near the center of the galaxy with millisecond accuracy. A millisecond is an incredibly small angle, like observing a coin from thousands of kilometers away and tracking its movement. By measuring how stars wobble, speed up, or slow down, scientists can map the invisible gravitational field and calculate the mass and size of Sagittarius A. These observations have confirmed that the black hole contains about 4 million times the mass of our Sun, concentrated into a space smaller than Mercury's orbit. Sagittarius A's gravity also interacts with magnetic fields and charged particles. Near the black hole, gas and dust are ionized, meaning the atoms lose or gain electrons, creating charged particles. These particles follow curved paths along magnetic field lines, producing radio waves that can be detected by observatories on Earth. Studying these emissions reveals how gravity and magnetism work together to shape the environment around a black hole. Some scientists believe that magnetic fields may even help funnel matter into the black hole, guiding its growth over millions of years. Gravity near Sagittarius A* also provides a natural laboratory for testing Einstein's theory of general relativity. In 2018, astronomers observed a star called S2 as it made its closest approach to the black hole, passing just 17 light-hours from the event horizon. The star's orbit bent exactly as predicted by general relativity, confirming that massive objects warp space and time in precise ways. Observations like this allow scientists to test theories that cannot be replicated on Earth, bringing us closer to understanding the fundamental laws of the universe. The gravitational influence of Sagittarius A* also explains some mysterious cosmic phenomena. For example, the Fermi bubbles, giant outflows of energy extending tens of thousands of light-years above and below the galactic plane, may have been created by past activity fueled by matter falling into the black hole. Similarly, high-speed gas streams near the center, moving at thousands of kilometers per second, are shaped by the gravitational tug of Sagittarius A*. By studying these features, astronomers can reconstruct the history of the black hole and understand how it shaped the Milky Way over millions of years. While Sagittarius A* exerts immense force, it does not directly threaten Earth. The stars, gas, and dust near the black hole are far away from our solar system, and gravity decreases with distance. Our Sun, 26,000 light-years away, remains safely in orbit around the galactic center, influenced by the combined mass of stars and dark matter as much as by the black hole itself. Yet its presence is felt indirectly in the stability and motion of our galaxy, reminding us that we are part of a system controlled by forces far beyond our everyday experience. Finally, gravity gives us a sense of the scale of cosmic time. Stars near Sagittarius A* orbit over decades, while the galaxy itself evolves over billions of years. The black hole grows slowly, swallowing gas and dust, and influencing star formation over millions of years. Observing these slow, majestic processes gives astronomers a window into the life of the Milky Way, showing how even invisible forces shape the universe over incomprehensible spans of time. One of the most striking features linked to Sagittarius A* is the Fermi bubbles, discovered in 2010 by NASA's Fermi Gamma Ray Space Telescope. These enormous structures extend roughly 25,000 light-years above and below the galactic plane. They are filled with high-energy particles and emit gamma rays, the most energetic form of light. Scientists believe these bubbles were created by intense activity near the black hole, likely from matter falling in millions of years ago. The exact cause is still debated. Some suggest it was a massive influx of gas feeding the black hole, while others think it could be the result of a burst of star formation near the galactic center. Either way, the Fermi bubbles are evidence that Sagittarius A* has not always been quiet. Black holes like Sagittarius A can appear dormant for thousands of years, then suddenly flare with energy when they consume matter. These flares occur when gas clouds or stars venture too close. As matter accelerates toward the black hole, it heats up to millions of degrees, emitting X-rays and gamma rays. Observatories like Chandra and XMM Newton have recorded dozens of these flares over the past 2 decades. One particularly bright flare in 2019 was about 150 times more luminous than the black hole's usual emission, a reminder that even quiet black holes can suddenly release enormous energy. Gas clouds moving towards Sagittarius A* can take thousands of years to spiral in, but when they reach a critical point, the energy released can affect the surrounding galaxy. These events can push gas outward, trigger new star formation, or even sweep away material that might have formed new stars. Observing these processes helps astronomers understand how black holes regulate the growth of galaxies. In other words, while black holes are small compared to the galaxy, they have outsized influence, controlling the flow of gas and the pace of star formation. Sagittarius A's past activity is also recorded in X-ray light echoes. When a powerful flare occurs, the X-rays illuminate nearby gas clouds, which then reflect the energy toward Earth. By studying these reflections, astronomers can trace flares that happened hundreds of years ago, giving us a historical record of the black hole's behavior. Some echoes suggest that Sagittarius A was much more active a few hundred years ago, shining like a miniature quasar, a type of extremely luminous black hole seen in other galaxies. This indicates that even today's quiet black hole has a dynamic history. Besides flares and bubbles, Sagittarius A* affects its environment through jets and outflows. Although smaller and less prominent than those from supermassive black holes in other galaxies, these outflows are streams of high-speed particles pushed out by the energy of infalling matter. In 2013, astronomers using the Very Large Array VLA radio telescope detected a faint jet extending from the black hole, showing that matter doesn't always fall directly in, it can be redirected outward, carrying energy far from the galactic center. These jets may play a role in shaping the Fermi bubbles and other large-scale structures in the Milky Way. Even the stars near Sagittarius A are influenced by its past activity. Some stars are arranged in tight disks, orbiting the black hole in coherent patterns. This arrangement may have formed from gas compressed and heated during earlier energetic events. Other stars, called hypervelocity stars, have been ejected from the galactic center at hundreds or even thousands of kilometers per second. These stars act as cosmic messengers, revealing how past gravitational interactions and energetic outbursts reshaped the galactic center. Astronomers also study infrared and radio emissions to understand past activity. Infrared light penetrates the dense dust near the black hole, allowing telescopes to track stars and gas in detail. Radio waves reveal the motion of charged particles, tracing magnetic fields shaped by energetic events. By combining data from multiple wavelengths, scientists create a multi-dimensional map of Sagittarius A's influence, showing how past eruptions affected not just the immediate surroundings, but the entire central region of the galaxy. The study of Sagittarius A's activity also has broader implications. Observing how our own black hole behaves provides insight into how other galaxies evolve. Most galaxies have supermassive black holes at their centers, and many go through active phases, shining as quasars or releasing powerful jets. By examining the Milky Way's quieter black hole, astronomers can understand the full life cycle of black holes, periods of dormancy, sudden flares, and long-term influence on the galaxy's structure.